Hello and welcome to Mellow Labs. On today's episode, I'm giving my fan a smart upgrade. So I've had this fan for a few years now, and honestly, it does the job of blowing me very well, especially during the summer months where I basically need this fan on 24/7. I'm a very warm boy. It does it very reliably. It has a few settings to do that, so if I turn it on, I don't love these buttons. They're very cheap, and this one keeps sticking, but it has the usual turning mode. We have a couple different fan speeds, and we have like novelty modes where we have like a breeze, where it kind of like ramps up and ramps down to pretend to be a breeze. And then we have the sleepy mode, and then the mode I use like 90% of the time, which is the actual like quietest mode available. It also has a timer, but I never ever use that, but it's there in case I ever feel like I need a timeout. It also has a remote which does all of the same things, but the main thing I want to do today is actually incorporate this into Home Assistant so that I can actually turn it off and on and trigger the different modes inside of my Home Assistant dashboard. And I want to do it so that I actually see what mode it's on inside of Home Assistant, and when I press a button in Home Assistant to change mode, it actually reflects on here as well. So basically just a full Home Assistant integration. I don't know how this works on the inside, so let's take it apart and have a look. I started off by just taking bits off of the fan so that it's easier to operate on when it's on my desk, and then I remembered that I should probably turn the power off and unplug it before I go poking at the electronics. But then to get to the electronics, I needed to undo the 3 screws that are at the back and the bolt that goes all the way through the main base over to the head because it's clipped in there. And then using a spudger, I kind of went around and undid the clips, which released the front face and showed me the PCB. And then, like with most of my projects, I took a bunch of photos of the inside so I know exactly where to put the wires back when I go to reassemble it. And then I thought to myself, you know what, I want to have a look at the motor as well. So I took out the one screw that holds the plastic shell over the motor, and in here it's not particularly interesting. There's a big ass capacitor, there's a motor that tilts the fan left and right, and the much bigger motor which actually spins the fan blades. And yeah, there wasn't much to do here, so all I did was add some 3-in-1 oil to the actual bearings, and it did actually feel smoother than it was before, so I guess it just needed a lube up after all the years of running. And then I just closed it back up and continued on to the electronics. I'm going to attempt an impression of a certain bear from the Isle of Man. Unfortunately, my electronics knowledge is significantly more limited than his is. So is my beard size, but let's not talk about my insecurities. This is where the live voltage goes in, and then we have a bunch of transistors which turn on and off the different settings on the fan head itself. We've got swivel, high speed, low speed, medium speed, and then W, which I have no idea what that means, but I'm sure it's important. Here is a bunch of AC filtering stuff, which then steps it down to DC. You can tell because there's a bunch of cutouts in the actual PCB to stop the high voltage arcing across. And then I believe it's stepped down using this MOSFET, which has absolutely 0 rating on it, but I assume it's some kind of MOSFET because all of the pins on this side are connected to one pad, which is pretty typical of a MOSFET. So then that steps it down to 5 volts for all the rest of the electronics, like the LEDs, the buttons, the resistors, and all that stuff. And it goes to this little microcontroller here, which I've not looked into yet, but I will. But I'm pretty confident that I can actually do what I want to do with it because the programming pins are actually broken out here. And that's really promising because it might let me actually talk to it directly. Before I disappear to find a datasheet for this little guy, I want to talk about this PCB itself because it's quite impressive. This is a single layer PCB, which means all of the traces are on this one side. On the other side, we have a bunch of components and a bunch of jumper wires which just jump over whenever there's traces involved. Usually you'd have a mask for this side and a mask for this side with separate jumper wires here, but this is a great cost-cutting method because you only have to design one side and then here you just put in a little wire. This is actually just a great way to have a low-cost PCB that I wouldn't have come up with all by myself. And now that you know about it, maybe consider making a PCB of your own using today's sponsor. JLCPCB offers easy, affordable and reliable PCB and PCBA services. Simply upload your Gerber files to JLCPCB.com and get an instant quote. 1 to 8 layer PCBs start from just $2, and right now there's a special deal for 6 layer PCBs where you can get a $30 coupon which brings down the price of the 6 layer PCBs to just $2. And they'll even include an ENIG finish and no engineering fee for veer-in pad. And if you're worried about quality, just don't. JLC PCB owns 5 state-of-the-art factories with quality control at every step. And if you need your boards right away, JLC PCB offers a lightning-fast 24-hour turnaround time. So sign up with the link in my description to get $123 in new user coupons. And thank you again to JLC PCB for sponsoring this episode. Okay, thank you for waiting patiently and letting me pay my bills. I found the data sheet for this 8-bit microcontroller, and if I go down to the block diagram, we can see that it does actually have SPI, which is Serial Protocol Interface, which basically just lets me reprogram the chip. Unfortunately, to do so, you need one of these programmers, which I don't have and I'm probably not going to buy. But why would I need to reprogram it? Well, I did some probing around and there's nothing coming out through the actual serial protocol here, which means that the script that's running on here doesn't actually output any information over serial because it's not configured, which basically means in order for me to do it the way I wish I could do it, like talking to the chip directly, I would have to pull off this chip, read the script, reprogram it, and then put the chip back. And that's assuming that they didn't use write protection on this chip, which basically would block it off to only running the one script that they've programmed on. So I'm gonna have to come up with a different way of doing it. Well, that's a bummer. So because I can't use SPI to communicate with the microcontroller, because for some reason they didn't feel the need to program a serial protocol into a fan, which, come to think of it, kind of makes sense, but it just means that I can't directly communicate with this microcontroller, like sending it commands and receiving commands back. So instead, my only main option is to use button emulation. I'm probably going to grab a microcontroller and see if I can actually emulate some buttons, which is very annoying because it's extra hardware that I have to use for this now, because instead of just connecting to the microcontroller and talking to it, I now have to have a GPIO thing for basically everything I want to do. So in this case, it's 1 per each button, which is 1, 2, 3, 4, 5, and then 1 for each of the LEDs so that I can actually sense what state they're in. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's quite a lot of buttons. It's very annoying. However, there is one more thing I could do. So it does have an IR thing for the remote control, right? So really, I could just emulate being the remote. So if I connect a microcontroller to the IR receiver and just send it the same commands it expects from the remote, I should be able to still put it into the same states. And then I'd still have to read the state of the LEDs to actually know what mode I'm in. But like I mentioned previously, I never use the timeout LEDs, so that narrows it down ever so slightly. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 GPIO pins is a lot more manageable. So I'm gonna go and do a little bit more research into that and see where I end up. My next step on the fan automation journey is to actually get the codes that the remote sends to the fan to, turn it off and on and change the modes and all that. So what I have here is an IR receiver connected to an Arduino, and I'll leave the guide I used on how this actually works. It's a very basic script, but basically all it does is it gets the code from the remote and prints it out in the terminal in raw hex format. So if I press that, we have some code. So now I'm going to make a quick note of that under the on and off switch and basically do that for all the other buttons. Okay, and with that we should have all of the raw button data that the remote sends over. So now let's switch this to a IR transmitter and see if we can pretend to be the remote with the Arduino. Shit. Okay, let's hope it still works. Oh, shit. Fuck. So you know how I very commonly point out the fact that I'm an idiot and you should not actually take any kind of advice from me? I think I just fried like the entirety of the board. Well, I think I fried the main microcontroller and probably some other bits too. So I was doing some testing, I had it plugged in, but I had the plug turned off, so no power was going to it. Unfortunately, turned off apparently doesn't mean the same thing as unplugged, because then I tried soldering on a wire to the ground plane so that I can actually like clip onto it, which caused a spark and then turned off everything in this room. And now it no longer turns on, like at all. So I can plug it in, I can turn it on, but it doesn't do anything, and none of the buttons do anything. I've tested the LEDs. The LEDs all still work. Power delivery is a little bit wacky. It seems to deliver 5 volts and then stops for a bit, and then delivers 5 volts and then stops for a bit. So I'm not sure where to start looking. I have a feeling power delivery, but I've also tried injecting 5 volts directly off of my bench power supply into the processor to see if it actually like boots on or anything like that, but it didn't, which makes me think it's dead. And now I have to explain to my partner why our fan is no longer alive. Hey, bub. Hello. Okay, so I had a little more time to actually go through things thoroughly and see whether things are still working. The processor, I mean the microcontroller, is just completely dead. The AC side, however, after some poking and prodding, seems to work fine. If I go to ground and then this pin, we get 11 volts. And then on the actual 5 volt rail here, we still get a steady 5 volts. However, the microcontroller just does not work. It doesn't do anything. When I plug the fan in, what it actually does is it sticks on, and the rotating is on as well. And that's it. You can't actually change anything. So apart from the actual microcontroller here, everything else seems to work okay. The next thing I actually want to test is whether I can, if I desolder this chip, does the fan stop spinning? So I'm gonna desolder this chip and see if the fan continues misbehaving. Now, when I turn it on, the fan should do nothing. Okay, that means whatever pins were stuck on are no longer on. Let's see if we give these transistors like 3 volts or 5 volts, if they actually kick on. I've got my power supply connected to the ground, and I've got 5 volts at the end of this probe. So if I turn on the fan, and now I should probably check which one of these does what. Nope. Nope. Nothing. Does it need more? Does it need like 10 volts? Okay, so it's 10 volts that it needs to actually operate. That should be, I think, high speed, medium speed, low speed, and I actually have no idea what W stands for still, but some kind of fan mode. Okay, cool. Okay, so it still works. I just have to find a way of giving it 10 volts. Okay, so I have some small but very good news. So I did some testing and I put 10 volts on these pins earlier in order to get the transistor to switch through and turn on each of the functions. Turns out I was being silly. I just needed ground. So if I connect this probe to ground and then connect it to one of the features, it actually works. So I was being very stupid. I didn't need 10 volts. I just needed ground. That's a lot more promising because I can manage pulling a pin down to ground. The normal state for these is actually at 5 volts. I measured that. So I can just pull them down and it will work. So I'm gonna go and map the rest of these things to see if I can actually, maybe substitute the original microcontroller with something like an ESP32. It's pretty late, I'm pretty tired, but I no longer feel as dark and gloomy about this project as I did earlier today. I spent a whole bunch of time reverse engineering the schematic of this board, and I basically managed to map the LED matrix, map the button inputs, and all the rest of the transistors for the actual fan control and everything. So I'm pretty confident that tomorrow I might be able to actually hook up a microcontroller to this, like an ESP32, and get it to be controlled by it with the same buttons and the same LEDs. So it's basically doing everything that I planned not to do when I originally started this project. Welcome to Storytime with Mello, because I didn't record anything yesterday even though I worked from 10 to 11 p.m. But I got to a decent place with the board, so let me walk you through everything I did yesterday. I started off by getting the LED matrix to work with the ESP32, and that was pretty easy. It worked after I accidentally burnt an LED by putting 5 volts through it, so then I had to replace it with a yellow LED because I didn't have any orange LEDs, but I don't think you'll be able to tell when it's actually in the enclosure, so we're all good on that front. Then I got all the buttons to work, and that was pretty trivial. It's buttons and a microcontroller. Pretty easy. Then I moved on to getting the transistors to work with the ESP32, and at this point I ran out of GPIO pins, so I had to make a choice. I could either get like a multiplexer for one of the features, or I could switch platforms to a Raspberry Pi Pico W. I went with the Raspberry Pi Pico W. I don't know how this is going to affect my Home Assistant integration. I know there is an ESP Home thing for Raspberry Pi Picos, but I haven't played around with it yet, so I guess we'll find out later. So then I had to transfer all of the LEDs and the buttons and all that code onto the Raspberry Pi Pico, but I got to do that in MicroPython, so it was pretty easy. And then I ran into a problem whilst trying to implement the MOSFETs that control the AC stuff, because they all run on 5 volts, and the Pico and the ESP32 run on 3.3 volts, so I would have run into this problem anyway. But I basically had to make an array of MOSFETs that will be controlled by 3.3 volts that can then control the 5 volts. I ended up using the 2N7000 MOSFETs. They're good enough for this, and it seems to work fine. I got the LEDs, the buttons, the MOSFETs, then I actually got the IR reader to work. Unfortunately, I don't know if the IR reader that was on the board was broken, or I just didn't know how to implement it, because I could not get any readings from it. So instead, I replaced it with the one that I got on the prototype PCB board. So I just desoldered it from the prototype board and then soldered it onto the main board, and the pinout was exactly the same, and hooray, it worked. Awesome. Then I moved on to the buzzer. I don't actually like the buzzer. The first time I got the fan, I actually filled it with blue tack because it was very annoying every time I plugged it in or pressed the button. But I figured, hey, I've got the GPIO pins to spare, I'm gonna make that buzzer once more. And so I did. So now, all of the individual things work. Let me demonstrate. So I currently have a test script running that cycles through each of the MOSFETs and, does all the functions that the fan does. So we've got high speed, low speed, medium speed, and whatever the W speed is. Apparently that's the quiet mode. And we also have the actual head tilt mechanism. I would like to test this whilst being connected to my computer, but if I run the AC stuff at the same time as being connected to my computer, the breaker is going to pop again. So I had to set this to be the main script so that it actually runs through each of these. So I'm not 100% sure which of the MOSFETs does which of the features yet, but I'll figure that out later. But I'm happy that that works. Now let's disconnect that and do the other functions. Here I have the LED test script, and as you can see, it's running perfectly. You can barely tell that one of the LEDs is yellow instead of orange. I really don't think you'll be able to notice when it's in the enclosure. Now I'm running the test script for the buttons, so when I press the buttons, it actually tells me that I'm pressing the buttons. Yeah, this one's pretty trivial. Now I've got the remote control and I'm running the test script, so if I press on and off, fan speed, head turn, timer, quiet mode, it all works perfectly. Love to see it. This one I don't think I have to explain. That's all of the individual functions, and at this point you're probably wondering, there's one thing you haven't mentioned. What's this guy doing here? This is an AC to DC converter. It specifically makes 5 volts at about 500 milliamps. It's not a lot, but it's more than enough for this. And why do I need it? Well, I was going to power the Raspberry Pi Pico off of the AC to DC converter that's already on this board. But unfortunately, even though every time I tested it, I got a steady 5 volts until I actually went to plug in the Pico to like get power off of it, where it just went to 0. Anytime when I disconnect the Pico, we had 5 volts. When I connected the Pico, it went to 0. So it just cannot sustain any kind of load. So I desoldered the little MOSFET that was on here because clearly it wasn't doing its job anymore after getting zapped. So I had to add in my own power supply. I had a few of these laying around. They work great. They do tend to be a little electrically noisy. I watched a video about it recently, but for this kind of situation, I think it's going to be just fine. And now I can actually move on to making one big script that does all of the things, and we will be back at stage 1, where the fan does all of the things it did before I put my creasy little fingers into it. It's done. I made one big script that makes everything happen, and we are officially back at square one, where we were before I decided to fuck everything up. So if I turn it on, it spins. I can change the speed just like I could before. I can go into different modes like I could before. I can even turn the timer on, and yes, it does actually turn off the fan after the set amount of time. And we can also turn on the swivel, which means now I can work on the Home Assistant integration, which in a way is now easier after I did all of the hard parts. If it actually works, I still don't know. Let's find out. I've been going at this all day now, and it's just not working with Home Assistant. I've tried multiple ways of getting this to like communicate and be controlled with Home Assistant, and it just does not want to work. Even the dumb ways of doing this don't want to work. The first thing I tried was installing the Pi version of esphome, and that worked. The install was pretty easy. It's pretty much just follow the instructions and you'll get there. And that worked. I got most of the code translated into esphome, and again, that mostly worked. Unfortunately, it doesn't support charlieplexing, which is what this LED matrix is. It's charlieplexed. So I can get the buttons to work, I can get it to control the MOSFETs, but I have no idea what mode it's in unless I look on Home Assistant, which would work, but it seems kind of weird if I can just look at the screen and know what mode it's in. So that's kind of a deal breaker for me. So then I thought, okay, what if I just add some kind of API thing to my Pi script that would let me over UART talk to an ESP32 and like work with Home Assistant that way. And that would work if at some point esphome didn't remove the ability for the ESP32 to read messages over UART. I then tried multiple other ESP like 8266s just because, you know, maybe they've not changed that too much. Unfortunately, all of the ESP 8266s I have left over, the Wi-Fi just doesn't want to connect on any of them. So I'm kind of giving up. I'm finishing the video with a fan that works exactly the same as how the video started. I mean, if anything, that's kind of an achievement, right? I'm gonna go put this back together, and then I'm gonna take a long think about what I'm doing with my life. And with that, thank you very much for watching. Don't forget to like and subscribe. Support me on Patreon if you'd like to see more of this foolishness. And I'll see you in the next one. Bye. I feel too embarrassed to come back up.